All right,
I watched yesterday.
this is a quintessential differential equation. Go ahead, you can say hi to Jamie.
Hi, Jamie.
All right.
Hi, Jamie.
Hi, James.
I don't miss you, Jamie.
This differential equation says that the rate of change is proportional to the amount present. And this actually, there are a lot of different things you can think about that sort of behave this way. Money is one of those ways. When you invest money, the rate at which it grows is proportional to the amount of money you have. If you have a lot of money, it grows quickly. If you have a little bit of money, it grows slowly. Certainly, like bacteria, like a culture of bacteria, the more of them you have, the faster they grow. Kids are like that. Not us. We're a little too old, but little kids are like that, right? Right, like the more of the baby you have, right, the bigger the kid, the faster, like it's the growth curve, right? So like an infant is certainly growing, but when you look at like from 1 to 2, the kid grows a lot. From 2 to 3, they grow significantly more, right? So the bigger that kid is, the faster they're growing, up until a point, right? Or else we'd all be like 14 feet tall or something like that. So, all right, so we'd be taller than that. But there are a lot of models out there that behave in this way, that says the rate is proportional to the amount present. So we're going to solve the differential equation. What do we got first?
First, let's put ky over 1.
Okay.
Cross multiply.
I'm going to keep the k on this side. You don't have to. You could actually do the 1 over ky, and that would be totally fine. I'm going to keep the k on one side, and the 1 over the y on the other side.
Wait, if you do 1 over ky, do you have to do dx over dy? So dx over dy equals 1 over...
No, what? If you're going to do... there's no algebraic help to do this. Right? Like, and now you're going to multiply both sides by dy, right? Like, so I guess it's an intermediate step that I don't think fine. Yes, exactly. That's what you would do. All right. We have 2 equivalent expressions, so we can take the integral of each side. Both sides here are actually fairly straightforward. The antiderivative of 1 over y?
Negative 1/2.
Just ln.
ln of absolute value y, Eva.
C1.
Okay. And over here, the antiderivative of a constant with respect to x? All right, so I'm going to change this to the absolute value of y is equal to kx plus some other value of c. I'll call it c3 if you want.
ln.
Oh, yeah, sorry. I totally forgot
What
that.
happened to C1?
A constant and a constant is just another constant.
So it became C3.
You watched the screencast last night, Alicia? Because I did. Aaron!
That's great.
Like Aaron.
All right. All right. So we get this, and I want you to notice that I'm actually holding on to that absolute value sign, and I'm going to tell you when I'm going to drop it and why I'm going to drop it in a second, but I'm going to keep with it for now. The next step we did yesterday, we said maybe taking the step forward was a little hard, but certainly taking it backward. If I told you what's e to the kx times e to the c3, if we have the same base, you'd tell me to do what with the exponents? Add the exponents. So, another way of thinking about e to the c3, what's e raised to a constant? C4, some constant. And at this point, I'm just going to call it c. Good.
Oh, yeah,
Good.
How does that C migrate down?
E to a constant is just another
another
constant.
constant.
It doesn't matter what the value of the constant is.
I don't get it. Sorry, say that again.
So, like, really, you could write C4 next to it.
If you want it.
If you want me to.
Why?
Because it's a new constant.
We started with
You
the
did the
first thing.
C4, it's just another constant.
Go ahead. One of you.
You
Listen,
go, Mike.
listen.
Wait, are you asking why?
We started with the first constant,
Yeah.
and we have to get on the other constant on both sides.
Because you multiplied them.
What's e raised to some number?
E to some number.
Yeah.
Yeah.
Constant.
So then why is there still an E there?
That's from the E to the kx.
E to the kx that doesn't change. That's e to the kx. But
Okay.
e raised to like 5 is something. It's some number.
The homework makes more sense now.
And I'm just going to call it c.
E to the 5 is about like 148.
Okay, Mr. B, don't you think couldn't you also just, like, before we even did that, couldn't you just, like, raise both sides to e, then you get rid of the ln of y?
I did.
That's what he did. That's how
You
we
told me to do
We
it.
got e to
You
the
still have
kx
y.
plus c3. Look how we got to
Oh,
e.
yeah.
Okay, c3.
Okay, I was confused with the ln.
All right. So at this point right now, because the absolute value of y is equal to a constant times e to the kx, the absolute value of y means I need to consider both positive and negative options. Like either y could be positive or y could be negative. The constant here takes care of that because the constant can be positive or negative. So now's the point where I can say, oh, guess what? Y equals c e to the kx. I don't have to worry about the absolute value signs. I can drop the absolute value sign. Many students don't necessarily understand when or why you can drop the absolute value sign. All they know is at the end, you don't need the absolute value sign. Just, you can stand out now, like next year, like when you're sitting in your math class, and you can explain to your class, your professor, if he or she asks, why and when you can drop those absolute value signs. Alright? And actually now, look at the function that we get. This is the solution. That's a pretty famous function from pre-calc, right?
Mm-hmm.
Part.
Isn't it PERT or exponential growth, or there's a lot of ways of saying it. So this actually ties together calculus, a differential equation, with something that we learned in pre-calculus that had a really important it had a whole chapter devoted on it, right? Exponential growth. So when you think about what we said about the differential equation, something that grows at a rate that's proportional to the amount that's present, that's exactly what the exponential equation says. The bigger it is, the faster it grows. It totally makes sense. That's nice, right? And I will agree, in an ideal world, we all would have stayed conscious yesterday, and I would have been able to show you the algebra. But it's okay, right?
No, it's not okay at all.
That was a beautiful drawing.
I'm sorry.
Did you get my email?
You edited that out.
I know.
All of a sudden, I hear, what was I doing? Where was I? And then I was like, why? Why did you do that? Why are you so nice?
So we would have stepped through the algebra of that. With that said, and this is just sort of like a note on resources available to you, I'm pretty sure the book had a problem worked out with like this algebra. So know your resources.
Well, I was using the solution guide, pretty not using the solution guide yesterday to try to but we weren't understanding because all of a sudden it would like jump from having
The con-
e to the kx plus b, and then it would have like y equals a to the
Okay.
dx.
So now
Oh my god.
so you saw it and now you actually know
Yeah, that
why.
was an outbreak of
Alright, good. Alright. Alright.